The equation E is equal to voltage times current times time is given to you in the back of the book. E stands for energy. It can also be shown as Q in the back of the book. This equation is a derivative of the equation that you have to know in your head. E is equal to Q times V. Q stands for charge, V stands for voltage or potential difference, and E stands for energy. There's another equation that you do have to know in your head. Q equals I times T. The amount of charge is equal to the current multiplied by the time. Because charge is a measure of how many electrons are carrying energy around the cell, current is a measure of the rate of flow of electrons around the circuit, and T we measure in seconds. If I've got, let's just say, 5 electrons per second, I would have 5 amps of current. It's not true, but we're going to say this. And my circuit's on for 2 seconds. How many electrons would have flowed past that particular component? How much charge would have been sent to that component? If I've got 5 electrons per second and this was on for 2 seconds, I would have a charge of 10 electrons. Now we measure it in coulombs. So we're actually talking about millions and millions of electrons, millions of packets of electrons all carrying energy around the cell. Circuit, pardon me. So Q equals I times T, E equals Q times V. Q is equal to I times T, so I can rewrite this equation. Instead of writing Q, I'm going to write I and T. Okay? E is equal to I times T times V. This is the same equation as this equation that's given to us in the back of the book. So they could ask us to use that, for example, in our specific heat capacity practical. When I've got a container of water, and inside that container of water, I'm going to put an immersion heater. My immersion heater is going to be connected to a power pack, 6 volts. And I've got to figure out the amount of energy that I'm giving to this immersion heater. How can I do that? I will attach a voltmeter to the immersion heater, and I will attach an ammeter in series. So the equation that we have for specific heat capacity, Q is equal to M times C times delta theta. So the specific heat capacity is equal to the mass times the specific heat the energy supplied is equal to the mass times the specific heat capacity times the change in temperature. What could I use to measure the change in temperature? Thank you, a thermometer. How would I measure the mass? Okay, I don't want you to say scales, I want you to say a balance, okay? A weighing scales works by tipping points from left to right. A balance is a measure of pressure upon a specific point. It's more accurate to use a balance than a scales, so we're going to say balance instead. I could measure the amount of energy using a joule meter, but they're expensive, they don't work very well, and we don't have one. So if I'm trying to find the specific heat capacity, I'm not going to be able to use a joule meter for this. So I've got to use an equation to find energy. E is equal to V times I times T. So, E is equal to V times I times T. E is equal to MC delta theta. What I can do is I can combine those two equations together, giving me V times I times T equals M times C times delta theta. Yeah, I can measure these very, very easily. I've got a voltmeter to measure voltage. I've got an ammeter to measure current. I'll have a little stopwatch to measure the time in my circuit. The mass I shall use my balance for. The change in temperature I'll use my thermometer for. And then I can find my specific heat capacity. Okay? So it's another time where we put two equations together. Another thing we might have to know about, power station and domestic supply. So this is my house. This is where the energy, the electricity is being generated. It's generally 25,000 here, 25,000 volts, and 230 volts at domestic supply. When it's sent over the wires, that supply is generally at 300,000 volts. Now I increase this voltage because it reduces the current. If I reduce the current, then I get less power wasted as thermal energy. The equation that shows me the amount of power that's being wasted as thermal energy, P is equal to I squared times R. Resistance, okay? R is resistance measured in ohms. Okay. I've got low resistance wires because they're really thick. They're made of high-grade metal. They're really thick. But I want my current to be low. This is what transformers do. Transformers increase voltage but decrease current. Where do I get this equation from? P is equal to I squared times R. And we all know Ohm's law, right? V is equal to I times R. Okay? This equation comes from this plus the Queen's pet cat called Viv. Power transferred is the current multiplied by the voltage. Voltage is current times resistance. So if I get those two equations, I can say that power is equal to current times voltage. Instead of writing this, I'm going to write that. So I can write that underneath as P equals I times R. I times I squared times R. So if they wanted, they might have given you the power, they might have given you the voltage and asked you for the resistance. There's no equation which links power and resistance, or power, voltage and resistance. But you would use P equals I times V to get the current, and then you could use V equals I times R, or you could use P equals I squared R to find the resistance, okay? That's what we call a synoptic question. When we're talking about transformers as well, so this is my step-up transformer. This is my step-down transformer. We know that step-up transformers increase voltage, decrease current. Step-down transformers decrease voltage and increase current. And that's because my transformers have got a primary coil and a secondary coil. My primary coil and my secondary coil, the power is the same. We assume that transformers are 100% efficient. So, P equals I times V over here will be equal to the power over here. Now, if I want to figure out what the voltage will be on the secondary coil, or the current will be in the secondary coil, or how much current I need to have here to make the secondary current a particular amount, I just get rid of the P's. So I would say that the current over here multiplied by the voltage is equal to the current over here multiplied by the voltage. But I'm going to get confused if I've just got I and V. So because this is my primary coil and this is my secondary coil, I'll say that IP times VP equals IP times VP. And if you look in the back of your test, you'll see that you've got this equation given to you. Now if they give you a 6-mark question on this and ask you, why does this equation work? How does this equation work? You can explain it now. You can explain it because there is 100% efficient. And this equation is the combination of powers. Yes?
On the equation, it's supposed to be add X and
Asa?
That was the exact same thing.
Making mistakes is a great way to learn. There's loads more synoptic questions, but these are a taste of ones that have either come up or I think might come up in the future. Okay? Anything else for anyone else?